Hi, good morning. So we're going to be going through some proper integral notations and applications. So we're going to do one application today, and then we're going to talk a little bit about notation. So big thing, this is the integral sign here. An antiderivative is the inverse of a derivative. So it's associated with taking the antiderivatives. We call that an integral. We notate the integral with the symbol to the right. It's basically a stretched out S. What I'm seeing is you guys are not using this symbol. There's no way for me to know what you are doing if you're not using the symbol. That's like you multiplying without putting a multiplication symbol, or dividing without putting a dividing symbol, or adding without putting addition symbol. You have to put the integral symbol if you are integrating. I will start marking you guys wrong if you're not putting the integral symbol. It's not magic that you find the original function from a derivative without doing the integral sign. So you have to write the integral sign. I'm going to start marking you guys wrong if you don't write or enter that integral sign on the Google Docs. Okay. So we can use this idea to find the original function given the derivative function. Again, we cannot find this original function if we don't use this integral sign. Okay. So down here, we have the indefinite integrals represent a family of functions that we can have made, okay, that have made this derivative. This C here is this constant of integration. The f of x is called the integrand, which is what's being plugged in. The differential is this dx that tells you what variable is going to be in your answer. And then the whole indefinite integral is this whole answer. Okay, so the differential, which is here, and the variable within the integrand, which is here, must always match. So if you have a dx, this also needs to be in terms of x. If you have dt, this needs to be in terms of t, which will also tell you that your solution will have a t or an x or whatever variable you are integrating with respect to inside. So be reminded that f of x is a derivative when you're plugging this into an integral sign. That's the biggest idea for you to understand. Since the inverse is, or the integrand is an inverse of the derivative, we have to have a derivative in order to use it. If we don't have a derivative, we cannot use this integral. And then once we put our derivative inside the integral sign, we do not need to use this prime notation anymore, since it is understood that we only have derivatives inside of the integral command. So this is the general idea that what we're doing is when we're using this integral sign, we're eliminating a prime from the derivative. So the integral of f prime of x is just regular f of x. The integral of double prime of x, like f double prime of x, is single prime of x. If I have the integral of triple prime of x, it is going to be double prime of x. And this is very, very useful when we're talking about applications. So for example, when we're doing free falling bodies, which is what we're doing on the next slide, position equations, we know that these are all derivatives of each other. We know that the velocity is a derivative of the position. We know that the acceleration is a derivative of the velocity. So now what we can do is use this integration to find them when they're not given to us. So up here, this is our free falling bodies equation. Okay, we have -1/2 acceleration times time squared plus velocity, the initial velocity, times time plus the initial position. Okay, so this is what we just said. Now, if I didn't have this function and I only had the derivative, so v of t, we would be able to integrate this derivative to obtain x of t. So that's what this big idea is we're going backwards. Now we're going to apply something able to go backwards. So the integral of v of t dt is x of t plus c. And then also the integral of a of t dt is the velocity. So if, let's say I only have an acceleration, I can integrate that to find its velocity. Then I can integrate that again to find its position. Okay, so this is our example that we're going to be talking about. So I have a ball is thrown upwards from with an initial velocity of 64 feet per second from an initial height of 80 feet. So let's say that this is my box. It's 80 feet. Sorry, I'm drawing with the mouse, so it's going to be really janky. So we have our ball. Here's the ball. Okay, it is being thrown upwards with the initial velocity of 64 feet per second, and then it's going to fall. So this Is there a way for me to erase? Yeah. Okay. So here we know that this is 80 feet. Okay, we're 80 feet in the air. We have 64 feet per second. And then it's 80 feet in the air. Okay, when does the ball hit the ground? That's what we're trying to figure out. Where's my mouse? Oop. This is what we know. Okay, we know the initial velocity or the initial position is 80 feet. We know that the S prime of 0 is 64 feet per second. So that's the velocity at the initial. Okay, and because the acceleration due to gravity is negative 32 feet per second, we could denote this as S double prime of t is negative 32. So what we're going to end up doing is we're going to use that second derivative in order to figure out the position. So I have the problem up here. So S double prime of t is negative 32. What I'm going to do is I'm going to integrate that. Okay, I'm going to integrate that because I want S prime of t. That's v of t in layman's terms. Okay, just to remind you, that's v of t. That's the velocity. So if I integrate this double prime of t, so I have integral of negative 32 dt, because I'm in t's, is equal to negative 32 t plus c. So that's my velocity function now. Okay, the next thing I'm going to do is I'm going to rewrite that. So I have S prime of t. If you're more comfortable writing v of t, that's okay. V of t is equal to negative 32 t plus c. Now, using that initial condition, we know that c is equal to 64. Okay, we know that its initial velocity is 64 feet per second. Now, we know that this could be S prime of 0. Okay, if I plug in 0 in here, I get 0. We have S prime of 0 is equal to 64. I plug in 0 into my t, I get 0. 0 plus c is 64. C has to be 64. Okay, so now we concluded that. I substitute it in. Bang, done. Now, I want to find out when the ball hits the ground. If I want to find out when the ball hits the ground, I need the position function, not the velocity function. So what I'm doing here is finding the position, which is the no derivative. I know this is terrible writing. I'm so sorry. Is equal to the integral of S prime of t. Now my next step here is I substituted in negative 32 t plus 64 dt, because I'm in t's, is equal to negative 16 t squared plus 64 t plus c. And this is my new position function. Okay, now that I'm in my position, I can use that initial condition that I got. So it has an initial height of 80 feet. So I know S of 0 is equal to 80. I know that looks like a 6. I'm sorry, it's not a 6. It's a 0. I'm going to cross it through so you know it's a 0. So if I plug in 0 into all of these t's, this will give me a 0 term. This will give me a 0 term. My c has to be 80. Okay, so now I have this beautiful function here. I have this beautiful function that I worked so hard to figure out. I'm just going to erase that so we could see it. And now your last step, which is something I'm not going to walk through because we did this all year, is figuring out when this ball hits the ground. So what you're doing is trying to find the zeros. Okay, you can use this equation to figure out when the ball hits the ground by factoring. You can factor out that 16. Oop, there should be a negative in here. Oop, go back. I'm going to write that negative in there. I actually forgot it. Apologies on that. So my answer is actually wrong. Negative 16. My bad. You could put this into Desmos. So let's go put this into Desmos real quick so I can show you how it looks. I'll keep these for my life. Okay. Go over to Desmos. If I go over to Desmos, what I'm doing is I'm going to take this equation. I'm going to remember to put a negative on it, just because I totally forgot to put that in my actual. Oop, did not work. So let's just put it in. I have S of t equals negative 16t squared plus 64t. Now what we can see is we have a 0 at -1, and we also have a 0 at 5. It doesn't make sense to use this -1 as a 0 because Can we have negative time? I really wish you guys could respond to me. No, we can't have negative time. So this does not make sense. Our whole trajectory, if we zoom out, we could think about our whole trajectory as this space here, right? So we start at this initial position 80, right? So you see a 0, 80. That's like where we're starting. We're on this hill, on this box, on this mountain. We throw our ball up. It hits its maximum height, it hits its axiom, and then it falls down. Okay. Since we're not in this negative space, we don't have negative time, we have to eliminate that 0, and then our answer is going to be 5. So my ball will hit the ground at 5 seconds. Okay. Thank you guys so much for tuning in. Please, please, please email me, contact me, text me. Let me know if you guys have questions, comments, concerns, issues. And it was really good to talk to you guys. I hope you have a great day and stay safe.